Hey everybody, welcome back to Bayesian statistics. Last time we finished by looking at a demonstration of Metropolis Hastings. Today I want to go through another very popular MCMC sampler called the Gibbs sampler. One of my favorite little factoids on the Gibbs is that it was popularized in the 1980s by, I think, a pair of brothers, Gemon and Gemon. But Gibbs is fairly different from Metropolis Hastings because there's nothing that gets rejected. You recall Metropolis Hastings, we make a proposal, we compute the acceptance ratio, compare it to a number between, random number between 0 and 1. If our acceptance ratio is above that number, we accept the new proposal and move to that location. In Gibbs, 100% of the samples are accepted because we guarantee to be sampling from the right posterior. How do we know that for a fact? We end up with known combinations of priors and likelihoods. And this is by no means an exhaustive list. This is just what I, when I typed in so-called conjugate priors, into Wikipedia, I came up with this list, and that is a fairly good list of common distributions. So the way to read this would be if your likelihood is normal and your priors are normal, your posterior is also normal. And the hyperparameters, right, these are the hyperparameters, and the parameters mix as written in line 1 there. The data is Y, and it interacts right in there inside the posterior distribution. The couple of cases that we'll discuss in more detail are the beta binomial and the normal inverse gamma. I will say that oftentimes to prove mathematically that Gibbs sampler works, that if in fact you have this kind of likelihood and this kind of prior, then you have this kind of posterior. To prove that the recipe works, it requires mathematical statistics. We're not a mathematical statistics class. So again, I'll be focusing on a fairly conceptual understanding of Gibbs. And we'll go through 2 examples in a little bit more detail. And I'll show you kind of common code from a software package called JAGS. Some of you may have heard of JAGS. It's very popular, probably the most popular Bayesian, standalone Bayesian software package that is accessible from R. Okay, with that, let's go back into a world that I think we're at least a little bit familiar with. This is straight from our activity 1. And so this is our random coordinate globe toss example. Their observed proportion is 14 out of 20. Remember that our likelihood was a binomial where n is equal to 20. And the prior that I used, which we showed was weakly informative, was a beta 3, 1.5. According to the recipe, according to this recipe right here, if I use a beta prior with parameters alpha and beta, now in R these are called shape 1 and shape 2, my posterior is also a beta, where my new alpha parameter is my hyperparameter alpha plus the number of successes, and my beta, my new beta parameter, is my hyper beta parameter plus the number of failures. So what that translates to in the context of land and water is that number of failures is the number of land observed. So it just populates, right? Whatever I used inside of my prior, and by the way, all of our intuition about prior predictive simulation applies to the Gibbs MCMC. We just populate the new alpha and the new beta inside the posterior. No random sampling needed because the recipe says this works. So with 14 out of 20, my new beta, my posterior beta, with this as my prior, which we know is nice and looply informative, and conjugate priors are the ones that produce no posteriors in combination with known likelihoods. My new beta is a beta 17 and 7.5. So if I know for a fact that is my absolute true posterior, then I just randomly generate 10,000 samples from it. Look, I have a nice stationary trace plot, right? It's stationary because it has a constant mean and a constant variance. So we have converged for sure. My effective sample size is going to be near. It's good to review these concepts. Effective sample size is going to be near 10,000, if not exactly 10,000. And here is my posterior distribution. All right. The only thing I needed was addition, subtraction, and the recipe to make it work. No tuning, nothing is rejected. This took a millisecond to do, and this would have taken a millisecond to do in 1995 as well. So, you know, if you can make it work, it's really a beautiful thing. It's the beauty of mathematics that makes Gibbs samplers work. Now, in a little bit more mathy terms, with multiple parameters, that's how it works with one. With multiple parameters, we need what are called full conditionals, which are the distributions. These are the full conditionals, by the way. Distributions of each parameter holding all other parameters constant, and of course the data constant, because in a posterior the data is held constant. So the key is a Gibbs sampler builds your new MCMC samples one coordinate at a time. Gibbs is one coordinate at a time. The Metropolis Hastings and the grid approximation, every sample is a new k-dimensional coordinate, right? This is a new k-dimensional coordinate. In your homework with the Weibull distribution, your samples were coordinates on a plane that was the shape and scale posterior. In our skew normal example, each sample in the grid approximation was a coordinate in 3 dimensions, right? Think back to the cloud. So if we were to use a Gibbs sampler with 3 parameters, we would need to build each spot in the coordinates, right? The coordinate looks like x, y, z. So this would be our x coordinate. This would be our y coordinate. This would be our z coordinate. And as we're building the x coordinate, we're holding the other 2 spaces inside the coordinate constant. As we're building the y coordinate, you see we just propagate that theta 1 and we hold the other 2 constant. As we build up to the z coordinate, we propagate the other 2 into what is held constant. And we produce a sample from what is called a conditional distribution. Conditional on theta 2 and theta 3 and the data. Conditional on theta 1 and theta 3 and the data. Conditional on theta 2, theta 1 and the data. That is different than the way we sample from the full posterior using grid approximation and Metropolis Hastings. Metropolis Hastings builds this equation using our successive samples, successive proposals of thetas, and then computes the acceptance ratio, either accepts the move or doesn't, right? Okay. Let's take a look at a couple of visualizations. this is just some of the most commonplace visualizations of a Gibbs analysis. In no way will this be exhaustive, but it just so happens that if you are working with a two-dimensional normal distribution, so a two-dimensional multivariate normal, each conditional distribution is normal. All right, these are our conditional distributions. And so this sort of tells us that to go from our starting location to the next position, our vertical separation, our vertical placement will come from this normal distribution, and then our horizontal displacement, our horizontal placement will come from this normal distribution. They are two different normal distributions, and you will see that they have equivalent standard deviations, but different means. We see some kind of a residual type situation happening right there. But the standard deviation is the same. So I like to think of Gibbs as almost like square dancing, because we take necessarily square steps. We update one coordinate at a time, and we're taking square steps. That is different than Metropolis Hastings, where we're not taking square steps because we're generating a random proposal from usually a multivariate normal. So they are mostly diagonal steps in a Metropolis Hastings. So, enough arm waving, let's look at some code. One of the most famous conjugate prior examples, again, conjugate priors. If we set priors a certain way, we know the full form of the posterior. So if I just kind of look at a relatively simple case, and I kind of revert back to the example from the book, where we just have a constant mean and a constant standard deviation variance, I need to set my priors a certain way in order to apply the recipe, in order for this recipe to work. And the way I set my prior is I set the prior for the variance. Note that it's not the standard deviation. I need to set the prior for the variance. And it's not even, you can think of it as setting an inverse gamma prior on the variance, and then it makes the posteriors look like so. Or you think of setting the prior on the precision. Inverse variance is precision, and most often it's written as a tau, but don't quote me on that because I haven't seen every single textbook. Inverse variance gets a gamma distribution, or that is identical in saying that the variance gets an inverse gamma distribution. An inverse gamma distribution is literally just 1 over a gamma. The mean of this likelihood, right? Everything, the parameters are in blue, so I need to set priors for this parameter and this parameter. The mean then gets a normal distribution, and that's why it's called a normal inverse gamma conjugate prior. Notice again that we're in terms of the inverse variance. And if we play this game, if we play the game with the priors, if we play the game with the conjugate priors, we get to just apply the formula, apply the recipe, the Gibbs recipe, and we know that our posteriors will look just like that. So we're just going to generate random numbers from a gamma that looks like this, a gamma where the first parameter is this and the second parameter is this. And we're going to generate samples for the mean from a normal where the mean is a hyperparameter and the variance is that. So let me flip back, let me flip to R. So there's a little bit of possibly weird code just to get access to the data. I'm going out to MacroGreek's kind of book website, and I'm reading the file that is out there, and I'm taking a subset of only the adults. This is a height data set. We're not interested in modeling height for children, so we just, to match what our author did, we read off our full data set, and then we're just taking the subset of everybody who is 18 or older. All right, so here is my outcome variable. Here's its histogram. It's nice and approximately normal. I'm going to record n, right? N appears in a number of different places inside of our Gibbs sampler. And because I'm doing this by hand, I have to make sure and set up my 3 chains, my 3 MCMC chains. Number of iterations, number of MCMC samples I will ask for. Remember that we're fairly certain we're converging to the true posterior only when this number gets large, right? This is true even when we're certain we're generating samples from the posterior. To get a good approximation for a beta 3.5, I need to take more than 10 samples. I need to take probably more than 100 samples. I need to take 10,000 samples. And so, although in a Gibbs MCMC, we are, because we're applying the recipes, guaranteed to be sampling from the right posteriors, we still should be taking something several thousand iterations. So iterations per chain is 5 times 3 chains. I will be taking 15,000 samples from my posteriors. I'm going to build an array, and so I need to specify the dimensions of the array. 2 parameters, 3 chains, and 15,000 iterations. All right. Remember, I have 3 hyperparameters to set. Which are my 3 hyperparameters? We still have to set priors, right? Let me clear off some of the drawing on this slide. So I have 3 hyperparameters. I have what I'm calling A and B inside of the gamma, and the mean of the prior for my likelihood mean. So it's worth it, I think, to spend a little bit of time talking about the hyperparameters of the inverse gamma, just because it is just so common. If you're reading literature, if you are using Bayesian analysis in a different class, it's just so common to run into the inverse gamma. It's 2 parameters, and if I look at the great resource called Wikipedia, here is the mean of the inverse gamma. Right? Here's my A and here's my B. And the other important one is the variance of an inverse gamma. When we're thinking about how informative something is, we care about the variance, but there's also a way to make your inverse gamma not have a mean. What would you set your hyperparameter to ensure that your inverse gamma doesn't have a mean? Well, you can set it to something like 1 or a number that is close to 1. If you set inverse gamma with alpha of 1, you will have division by 0 here, so an infinite mean, and the variance has alpha minus 1 in the denominator. You can set, if you set alpha equal to 1, you will have division by 0 in the denominator. You will have infinite variance. If you have an infinite variance, you have an uninformative prior. Do you want an uninformative prior? That's a question, that's a good question to ask. But I am a big fan of setting alpha equal to 2. I'm a fan of setting alpha equal to 2. Because if I set alpha equal to 2, I center my distribution at beta. You guys see that? If I set alpha equals to 2, the mean of my distribution will be beta. And then if I set alpha equals to 2, I can claim I have an uninformative prior, because with an alpha equal to 2, my variance is infinite. So although it is technically centered at some value, for example, the sample variance, right? I'm setting a prior for the variance. It's okay to center it at the sample variance. My prior variance will be infinite with alpha equals to 2. So I can claim I was uninformative. So I will achieve this, right? Here is my alpha of 2 and beta equal to the variance of y. So this inside of an inverse gamma means that I'll be centered at the variance of y, just 59.8, and my prior variance is infinite. Prior for the hyperparameters, right? The prior for the mean is normal, and the hyperparameter of that normal distribution, I can just center it at the mean of the data. That's a reasonable value. And I'll show you what happens if you set it at something silly like 0. Remember, we're modeling heights. Height of 0 is not only implausible, it's just impossible. I think our author calls it an embryo a few times throughout the book. All right, so let me run my MCMC setup and my hyperparameters. Here they are. Okay, so now I have 2 loops. Why do I have 2 loops? Because I'm doing something I'm looping over the chains. I'm assigning a starting value. Notice that in the notes, I make clear that there is a circular relationship. I draw an inverse variance out of a gamma distribution, and then I populate the distribution of the mean with my new sample. Then I take my mean sample and I plug it into the next inverse gamma, and we repeat some number of times, 15,000 times according to my code. So to start this process, I'm going to start it with a sample of the inverse variance. I need to give it a starting value of the mean. And here, yes, I certainly could put the starting value at the mean of y, but I want to show you what happens when you start it at something ridiculous like 0. Let me repeat just to make myself clear. The prior mean for mu, 0 is not a very good value at all, because a priori we can expect heights of adults to be greater than 0, quite a bit greater than 0 in centimeters. But to start our sampler, which will only converge to the true posterior after a certain large number of samples, it's okay to start it at 0. I am making this point until I'm blue in the face, right? We're starting somewhere off in the nether space. And then our sampler very quickly, in just one step on this picture, converges to the posterior distribution. So, and I will show you how that happens. So my first loop is over the chains. My second loop is over the iterations. I'm applying the Gibbs recipe, right? So I am building the posterior parameters of my inverse gamma. I'm applying this known recipe. I'm building the parameters of the inverse gamma. And here I am drawing a random sample from an inverse gamma. Yes, I know that there are R packages that have the inverse gamma distribution, but I am making it clear that there's nothing special about the inverse gamma. It is just 1 over a gamma. I'm taking a single sample, using my Gibbs recipe for the shape and a Gibbs recipe for the rate. Then I'm taking that sample, sigma squared sample, right? Sigma squared gets an inverse gamma, inverse variance gets a gamma distribution, and I am plugging it into the distribution of the mean. Notice that I have to invert it back to apply my recipe. And finally, draw the mu and save my 2 samples for posterity. No pun intended. This will run very quickly because there's nothing to tune. And here we go. Done. So let's see what we have created. I'm using the coda distribution. You guys have seen this before, so I won't explain it. Here, I'm excluding the first 500 samples because I started the sampler at a mu of 0, and that is a ridiculous number. So for the first bit, I'm not sampling from the posterior distribution. Let me go ahead and exclude this. Let me just show you what all of these samples look like. Okay. From iteration 1, the chain for mu looks legit. This is what we hope our trace plots look like. Chubby caterpillars, not slithering snakes. Chubby caterpillars, not slithering snakes. The distribution, the trace plot for mu is stationary. It has a constant mean and a constant variance. Very good. Look at what is going on with sigma. That was always going to be a more complicated process because we're taking an inverse gamma. We're taking an inverse of something. It looks like in the beginning, it's meandering a little bit. And then very quickly, very, very quickly, it plugs in and walks to the posterior. Notice this is very similar to what's going on here, where we started off right here at B, and then the first step is the right step. We're on the posterior after the first step. So this is simply a byproduct of our starting value being 0 for the mean mu. To see this even better, here are the first 10 samples. The first 10 samples from each chain. The first 10 samples from each chain. Well, it doesn't look too, well, that's why we take 15,000 to determine if we're sampling from the a stationary distribution. But look, the first 10 samples, right? It takes us, on the second iteration, we go from a ridiculous number to the right posterior. So, by excluding the first few samples, I probably could have gotten away with excluding the first 10, but it's typical to exclude the first couple of hundred. So I think I had this set up like this. This is called a burn-in. This is called a burn-in because this basically removes any effect that your starting values have on the Gibbs sampler. Now, once I exclude the first 500 samples as burn-in, rerun this. Notice I'm not resampling anything. I'm just looking at my 15,000 samples, right? I'm looking at my 15,000 samples, excluding the first 500. And I have some beautiful, beautiful trace plots. I get a stationary distribution for the mean, and I get a stationary distribution for the standard deviation. I expect my distribution of the standard deviation to be right skewed, and I expect the posterior distribution of the mean to be nice and normal. You guys have seen this before. Here is my posterior mean. Here is my posterior standard deviation. Here is my posterior credible intervals for the mean and the standard deviation. To recap, we assumed that our prior for the variance was centered at the true variance, but had a infinite prior variance based on the equation of the inverse gamma. My prior for the mean was a pretty good one. It was just a sample mean. Look at what happens if I mess up and I set the prior mean equal to 0, in addition to setting the starting value equal to 0. This will exclude the data a priori. Well, my posterior comes up with 0, but we know this is a ridiculous posterior for height, for adult height. And the reason why this happened was I simply excluded any kind of plausible range of values a priori because I wasn't particularly careful about how I set this prior. We can try and play around with the hyperparameters of the gamma. We can set them to be something fairly ridiculous, like 2, 1. This is now centered at 1 with an infinite variance. This will have a minimal effect, but it will have an effect. In fact, it had almost no effect on the posterior. So you can see that the posterior is not particularly sensitive to the prior for sigma squared, but it is quite sensitive for the prior for mu. Because look, now my sigma is estimating something ridiculous and my mu is estimating something ridiculous. So this is a part of what I call performing a prior sensitivity analysis, where you see how much of an effect your hyperparameters have on your posterior. Okay, so this code is out there for you guys to play around. So Gibbs is very popular. It was one of the first standalone software packages to introduce wide-scale Bayesian sampling. I believe WinBugs started circa 1993. And you can see it's, although bugs and WinBugs, although it's quite popular, it is starting to be on a little bit of a decline. By the way, all of these bugs, the GS in bugs, is Gibbs sampling. Now, where we're headed next time is this bottom panel, is this up and comer, right? Look, this is 2015, we're now in the year 2020. Stan, with its MCMC sampler, is gaining popularity, and I want to show you why. Similar to the fact that I'm not trying to convert anyone to be a Bayesian, I'm also not trying to convert you away from Gibbs sampling. Gibbs sampling is popular because it works in a lot of cases. What's wrong with Gibbs? In some cases, not a ton. It is more efficient than the Metropolis Hastings because our proposal never gets rejected. So we're never in the case where our chains are stuck or our chains never move. And you don't have to tune your proposal distributions. Tuning takes a long time. It's a publish or perish culture. So that's why we like Gibbs. We don't have to tune anything and our proposals never get rejected. It works just fine if you have a medium number of parameters. If you're estimating relatively moderately sized regression models, Gibbs will work for you just fine. Gibbs will work okay if your parameters are uncorrelated and their posteriors are hyperspherical. What am I meaning? I'm meaning that if we're working with posteriors that are relatively circular, then Gibbs will work just fine. Remember, Gibbs takes square steps. Square steps do a good job covering circles. Square steps do a little bit worse if our posterior starts to become more elliptical. And I'll show you a couple of slides to that. The other thing is, you know, when I was starting out doing some Bayesian analysis, you know, you read things, you read textbooks, you read things online, and everybody was using Gibbs. And I just had the toughest time because I couldn't for the life of me wrap my head around conjugate priors. You learn everything in terms of the variance until you get to a Gibbs sampler, and then they go, nope, nope, in our world, it's inverse variance. And you're like, okay, inverse variance, that means, in an inverse variance, that means if it's big, the inverse is small. Ooh, it messed with my brain. Maybe it won't mess with your brain, but when I was starting Bayesian analysis, Gibbs samplers messed with my brain. It's widely implemented. And I just want to show you just what an example of a JAGS code looks like. So this is just, I typed in linear regression in JAGS, and this is what a JAGS program looks like. I just want to point out that we can just read this. We've done this before in activity 2. This is a regression model where the mean varies with observation. Look at our activity 2, right? You have yi, it comes from a normal distribution where the mean depends on observation, and this mean is constructed from alpha, our intercept, and beta, our slope. And then here is a covariate. Their covariate, I don't believe, is centered in scale. Look at this, tau, right? Tau is inverse variance. So they're just telling you that to get your intuition about big and small numbers on the right scale. This is now working on an inverse scale. All right. For every observation, we do this, right? By IID, every observation comes from its own normal distribution with a unique mean that is constructed according to the regression equation. Again, looks very, very similar to our last activity. The priors. If you just look at this prior right here, look, you even write it in terms of the tilde. You're saying alpha is distributed according to a normal distribution with a mean 0. And what is this term? Yes, welcome to Gibbs. What is this term? The denorm command is parameterized in terms of 1 over the variance. So at first glance, this is a very informative prior, but in reality, it is not. It is, 1 over this value that is the variance of this normal distribution. So this is equivalent to setting a normal distribution centered at 0 and a variance of 100 for the intercept. This sets a normal distribution, mean at 0, variance of 100 for the slope. And look what they're doing. They're setting a uniform distribution for sigma because it's easier to set on the sigma level and then convert into a precision. So these are the types of gymnastics that happen inside of JAGs, open bugs, win bugs. The beauty is nothing to tune. Every sample comes from the right posterior. So you can converge right away. Just want to point out one more thing here. You have to start it at some initial values. Remember that I started at an initial value of 0. And look, they're using 3 chains, and change is 3. And iter, how many iterations they want. They're taking 12. I took 15,000, 12,000, I took 15,000. And they're treating the first 2,000 as burn-in. Remember, burn-in is to sort of remove the effect of the starting location on the Gibbs sampler. We're only guaranteed to have converged to our true posterior after a large number of iterations. We haven't talked about thinning yet, but they're going to record every 10th iteration to remove any serial dependence. Going through JAGS code is not really in the scope of this class, but I just wanted to put it out there because in my experience, students have already been exposed. A lot of students have already been exposed to JAGS in some form or another. And I just want to sort of point out that we can just read this right away as long as we know the gymnastics that are inherent to a Gibbs sampler. And this is probably the biggest one. Not all likelihoods have conjugate priors. So you need to make sure, if you're applying a Gibbs sampler, you need to make sure that you're using a conjugate prior. You can't use a normal likelihood and a T prior. I was grading a homework assignment. Somebody used the T distribution for the lambda parameter inside of a Weeble. You cannot Weibull. You cannot do that. You are limited by certain prior distributions in order to make the Gibbs recipe work. If you're okay with all of these things, then go ahead and use Gibbs. It's great. But, of course you knew there was a but. Gibbs is known to have problems. Gibbs is known to have very low effective sample size in complex models, where our successive samples tend to be autocorrelated. And here is an example. This is a plot of 2 dimensions, right? 1 dimension, 2 dimension, out of a highly correlated 250 dimensional multivariate normal. So we have 250 variables and a multivariate normal distribution with non-trivial off-diagonal correlations. We start with a metropolis, and it's just a failure. It's not going anywhere. It rejects a lot of proposals. It's not moving at all. You're not getting anywhere close, right? Here is the gold standard. Here is the truth. Just independent samples from the multivariate normal. The closer we look like to this, the better. Metropolis, just utter failure. Gibbs. Compare this plot with a plot we showed you earlier, right here. Oftentimes, it takes us a while to explore the tails. And that's because Gibbs takes square steps, and if our posterior distribution is elliptical, it will have trouble covering the whole thing. Look at Stan. That's where we're headed next. I am simply setting us up for next time. Look at Stan. It is very, very similar. It produces MCMC samples that are very, very similar to independent ones. So these have a nice, high, effective sample size. And we like that. So I keep saying Gibbs takes square steps. Gibbs takes square steps and it covers nicely relatively circular posteriors. But when your posterior is elliptical or worse, like a banana distribution, and I'll go back to the banana distribution in just a sec, it will miss the tails. It will refuse to go to the tails because the coordinates are updated one at a time, and it is stuck making square steps. I have a couple of more slides to sort of introduce what the Hamiltonian Monte Carlo looks like. Hamiltonian Monte Carlo takes I'll just write it down. Stan and Hamiltonian Monte Carlo simulates particle motion. And what you're thinking about when you're thinking of Hamiltonian Monte Carlo is flicking a marble in a bowl, right? We flick a marble in a bowl. And the marble goes this way, that way, this way, that way, and stops. So that's our preview for next time. I want to leave you with a demonstration of how a Gibbs sampler works. I am back to Chifeng's GitHub page. I've selected Gibbs sampler and the banana distribution. So first, I will start again at a random location. And I've just adjusted things so that they look better on screen. So when I take the step, it will first update my vertical component, and then it will update the horizontal component. Gibbs sampling updates one component at a time, one coordinate at a time, holding the other coordinate constant. All right, there it is, right? This particular case, we went this way first to update this coordinate, and then from here, holding now our vertical position constant, we went this way to the next MCMC sample. So our next proposal will come from this new location. And again, the green arrow indicates we have accepted. We know in a Gibbs environment, we never reject. All right, now I'm gonna say step. It will update one coordinate at a time. All right, we updated our horizontal position by holding the vertical position constant. And then from there, we update our vertical position holding the horizontal condition constant. And we took that as our next step. And now we keep doing this, and we'll autoplay and reduce the animation length to show you how Gibbs works. I think even visually already, it's doing a better job than Metropolis Hastings. First of all, there is never a red arrow. We're generating data from the right posterior every time. But you can see it's not quite exploring these tails all that much. And that matches up to what I've had in a couple of slides now. Right? It's taking square steps. It is not being responsive. Well, it doesn't see the blue posterior. It only sees the conditional posteriors. And so it's not being responsive to the shape of the posterior. Still, after all this time, we have a great indication of what's going on in the middle of the posterior. We have badly misrepresented the tails of this distribution. It just went there briefly and it has gone back to the middle of the distribution. By the way, if I change this to the donut, oh, not donut, excuse me, not donut, the standard distribution, this is the world where Gibbs sampling thrives. This is very similar to this slide. But our posterior is no longer even correlated. Our posterior is a two-dimensional multivariate normal where the correlation between the two variables is 0, right? This is just a simple anthill, a simple pimple, if you will. Look, the Gibbs sampler is doing great. We are getting samples in the tail, and we expect there to be fewer samples in the tail than in the middle, but we're actually getting out there in the tail. It's doing a good job of representing our two posterior distributions. We're getting a pretty good idea of that. Now, of course, I can mess it up even more. I can give it the donut distribution. Now, people say that in high dimensional space, the posterior distributions look a lot more like rings, like this, like donuts, than like either bananas or standard normal distributions. To be honest, it's doing a pretty good job here. But the Metropolis Hastings would fail miserably because it would constantly try and step off into the middle. Okay, that was a lot of material. Thank you guys for your attention. Next time, we will start with our third sampler that we will spend a lot of time on, which is Hamiltonian Monte Carlo. And yeah, thank you for your attention. I will see you all next time. Bye-bye.